All right, let's look at a scenario here. So for this scenario, it says you have a heavy pulley. A 15 Newton force, represented by Ft here, okay, is applied to the cord wrapped around the pulley of mass 4 kg. A radius of 33, this is radius, 33 cm. The pulley accelerates uniformly from rest to an angular speed of 30 radian per second in 3 seconds. If there is a frictional torque, which is 1.1 Newton meters, okay, at the axle, determine the moment of inertia of the pulley. Okay, so we are supposed to look for the moment of inertia, which is I, denoted as I. So what should I do? First, you draw out the free body diagram. Okay, so the diagram, as you can see here, this is the direction of Ft, and this is the frictional torque. Okay, so what do I do next? I can now start by saying that if I want summation of torque, it is equals to Ft times the radius minus with the frictional torque. Okay, so just put everything in. Force Ft of how much? 15 times R 0.33 minus the frictional torque given as 1.1. Simplify that, I got 3.85 Newton meters. Okay, now according to this, we know that we can find alpha from here, the data here, right? Because it moved from rest. Okay, so alpha is equals to omega F minus omega I over T. If you notice, this is your omega F and this is your omega I and this is your T. So put everything in. So 30 minus 0 over T, which is 3. So you get alpha as 10 radians per second square. Now, by knowing these, this is torque and alpha, I can now work for I. So the formula is torque equals I alpha. I'm looking for I. This is torque divided by alpha. So put torque, this divided by alpha, you will get I equals 0. Okay, I'm just going to write the answer, 385 kg meters square. See that? Now, you can also estimate. A rough estimation is you use the equation. Since this pulley is a uniform cylinder, so the equation will be half mr squared. So the mass is given to you. The mass is 4 kg. And the radius is that. So plug these in. If you plug all these values in, you get 0.218 kg meters square. So what is my final answer? So the answer is, this is I according to the rotation, right? And this is I estimated from the shape. Okay? All right, let's see next. Okay, let's talk about this. Rotational KE, rotational kinetic energy. Okay, if you recall, you know that KE equals half mv squared. And we know that V is equals to omega r squared. If I simplify this, I will get half mr squared omega squared, right? So I can change, again, I can change this. I can say that, hey, if this is half mr squared, I know that this is I. Therefore, Ke is half I omega squared. So we use this as rotational kinetic energy. So if it is rotating, okay, if it is rotating and it is moving, then it will have Ke rotational. Okay, This is KE linear. KEI or linear is half mv square. Just keep that in mind. Yeah? All right. Okay, so next question is, can we add them? Yeah, of course. We can say if the object is moving, then we can find its total, KE, by saying that it's equals to half mv square plus half I omega square. See, in this case, we're saying that it is rotating, right? This ball is rotating and it is moving in a straight line as well. So you will have to use both equation to calculate it. Yeah. So you use both equation to calculate the value of kinetic energy. So how can I calculate the kinetic energy? Let's see here. See, this question is saying that what will be the speed of the solid sphere, okay, of mass big M and radius R. If when it reaches the bottom of the incline, if it starts from rest with vertical height h and rolls without slipping. So it's just rolling like this, coming down, down, down until the bottom. So you can use E total equals half mv square plus half I omega square plus mgh. But I believe if it is asking at the bottom, then this is gone, right? See, this is 0. So then we can say that it is half mv square. Since this is a sphere, I have to go look for I of a sphere. So you can see here, I of the sphere is 2 over 5 mr squared. So I change that to 2 over 5 mr squared. There you go. Right? And omega is v square over r, v square over r. Simplify this. You can now find the v by equating it because this is asking for the velocity, right? So initially you have GPE, then it's all converted to KE. So simplify this, you cancels all the m's out and rearrange, you will get half plus 1/5 v squared equals gh. So you want v, so simplify this, cross multiply that, v is equals to square root of 10 over 7 gh. Okay, so this is some kind of a question that you may get. Please make sure you understand when to use rotational kinetic energy. All right, let's see. The work done by the torque is simply torque times the angle, right? So how much angle was rotated by the wheel? Just take torque, how much torque was applied. So torque here, this is work done. Torque is equals to F times the radius, F times R, and times the angle moved, change in angle. Okay, you can find the work done. How about power? If you want power, you just divide the work by time. That's all, right? You can now say, okay, power is torque times the angular velocity. Okay. All right. Now you are looking at angular momentum and law of conservation of angular momentum. So what is angular momentum? So we say that when the object is moving or spinning, it will have the angular momentum. It is calculated by using L equals I omega. So L equals I times omega. Okay, when you're moving. This is linear momentum. P equals mv. Okay, we are not looking at linear. We are now focusing on the angular. Okay, so L can be found using this equation as well. You can say L is equals to torque times change in time that it is spinning, the object is moving, right? And you can also denote it or equate it. We know that torque is I alpha, right? So according to law of conservation of momentum, keep in mind that this L I will equals to LF. So what does that mean? Look, total angular momentum, okay, of the rotation will always remain constant if the net torque acting on it is 0. This is the equation. So this was derived from the above here. So this is like I initial and omega initial multiplied out will equals to I final times omega final. Yeah? So this is always a constant value. So just look at this. This girl is spinning, right? So I can say L A will equals to LB. So this is A case and this is B case. This can also be equated by using MVR. This is R1, right? And this is V1 is equals to MV2R2. So this is the radius here is R1 and the radius here is R2, right? We can equate it this way also. Okay.